students, so welcome back to my video lecture 10 on P block elements. So students, from first video to 9 videos, okay, so we have completely covered the basics of P block elements, and also we have completely covered one block of P block. That is, what is it? One group of P block. What is it? 13th group. We have completed completely, successfully all the physical properties and chemical properties of 13th group elements. What is that 13th group elements called as? Boron family. We have completely finished it. Now, so in this video and in the next subsequent videos, we will talk about the next family of P block, the next group of P block, that is the 14th group. What is that 14th group elements called as? So in this video and in the next video, I'll be talking about the 14th group elements. 14th group elements. 14th group elements. What are these 14th group elements called as? They are called as carbon family elements. They are called as carbon family elements. So if you have understood the boron family very well, then it is easy and it is very easy to understand the carbon family elements. If you have studied, if you have seen my video lectures from video lecture 1 to video lecture 9 about boron family, then you have, it will become very easy, very simple to study the carbon family elements. Carbon family elements. So students, which are the elements of carbon family? Yes, in carbon family we have carbon, silicon, germanium, tin and lead, isn't it? So in carbon family, hope you can see this, carbon, we have carbon, silicon, germanium, tin and lead. I'm going to write it here so that it will be visible for you properly. So we'll have carbon, silicon, germanium, tin and lead. Tin and lead, is that correct? Carbon, silicon, germanium, tin and lead, isn't it? So these are the elements of the carbon family. Elements of what? Carbon family. We know in this case, out of these elements, silicon and germanium are what? Metalloids, correct? See, silicon and germanium are metalloids. Didn't I tell you about this in the previous video also, in the very beginning of P block elements? Correct. So we have learned the elements above metalloids are non-metals, and the elements below metalloids are what? These two elements are metals. Are you getting my point? Yes, the elements above metalloids are non-metals, the elements below metalloids are metals. That means to say carbon is a non-metal. We know this very well. Carbon is a non-metal, silicon and germanium are metalloids, tin and lead are metals. Tin and lead are what? Metals. Yes, and we know tin and lead are what type of metals? What type of metals are they? They are amphoteric metals, isn't it? Tin and lead are what type of metals? They are amphoteric metals. That means they react both with acid as well as base. Correct? So carbon is a non-metal. Silicon and germanium are metalloids. Tin and lead are metals. And what type of metals are they? They are amphoteric metals, isn't it? Very nice. Now, as usual, we have got to discuss about the physical properties, the chemical properties of carbon family, and also some of the important compounds of carbon and the important compounds of silicon. Yes, so in physical properties, what are the things that we discuss here? In physical property, we will talk about their electronic configuration. We will speak about atomic radius, and then what? Ionization enthalpy, and very importantly, if you have to understand the chemical properties, you should be knowing about what? Oxidation state, isn't it? Okay, so EC refers to electronic configuration, AR refers to atomic radius, IE refers to ionization enthalpy, and OS refers to what? Oxidation state. Oxidation state. So we have got to discuss all this chemical properties now. Okay, shall we understand? Sorry, all this physical properties. Okay, so shall we understand one by one? Yes. First, let us talk about their electronic configuration. Okay, if you know the electronic configuration very well, it is easy to explain atomic radius, it is easy to explain ionization enthalpy, and it will be very easy to understand oxidation state. Okay, so now let me talk about the electronic configuration of carbon family. So we have carbon, silicon, germanium, tin and lead. Is that correct? Tin and lead. Okay, carbon. Okay, we know the atomic number 6. 6 plus 8, 14. 14 plus 18. 14 plus 18 is going to be 32. So, okay, the atomic number of germanium is 32. Okay, 32 plus 18 is how much? Okay, it's 50. Is this correct? 50. Yeah, correct. Next, 50 plus 32 is, okay, 82. 82. The atomic number of lead is 82. Okay, so carbon 6, silicon 14, germanium 32, tin 50, okay, lead 82. Now, okay, be careful, very careful when you write the electronic configuration of these elements, because it is the electronic configuration which explains the various physical properties and the various chemical properties of any group elements, isn't it? Correct. Okay, now when I talk about carbon, what is its electronic configuration? Yeah, carbon 1s2, 2s2, 2p2. Is this correct? 1s2, 2s2, 2p2. Okay, while you write the electronic configuration, please observe the outer shell configuration. Okay, when you write the electronic configuration, please observe the outer shell configuration. What is the outer shell configuration of carbon? It is 2s2, 2p2. Now coming on to silicon. Okay, what is its electronic configuration? It is 1s2, 2s2, 2p6, okay, 3s2 and 3p2. Is this correct? Yeah, 3s2, 3p2. Correct. Now coming on to germanium, what is that we'll have? Okay, germanium 1s2, 2s2, 2p6, yeah, 3s2, 3p6, 4s2, 3d10, 3d10, how much over? Okay, yeah, 30, 4p2. Is this correct? Yes, 4p2, 4s2, 4p2. Okay, now still be a little more careful. Okay, 10, 50, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, okay, 30 over, isn't it? Yeah, okay, 4s2, yeah, 4p6, yeah, then 5s2, okay, yeah, okay, 5s2, after 5s2, what is that you're going to write? Okay, 4d10, isn't it? Okay, hope you remember the energy level diagram. Okay, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, okay, 5s, 5p, 5d, 5f, okay, and then what? Yeah, yes, okay, 6s, 6p, 6d, 6f, 7s, 7p, 7d, 7f. Okay, yes, go in this order. Yes. Okay, so we have completed 4s2, 4p6. So after 4s, 5s2 is completed, then 4d. Okay, so altogether how much over? Okay, so 2, 10, 10, 20, 30, 40, okay, yes, 48, yes, 50, 5p2. Okay, is it correct? 5s2, 5p2, isn't it? Now last, okay, yes, tin and lead. Okay, what is the atomic number of lead? It is 82. Okay, yes, very lengthy electronic configuration, isn't it? Okay, what's its electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, okay, 3d10, okay, then 4p6, and then 5s2, okay, yes, 4d10, okay, 5p6, after 5p, yes, 6s2, 6s2, after 6s, okay, we'll go with 4f14, 4f14, okay, after 4f, yes, it is 5d10, 5d10, after 5d it is 6p2, okay, 6, okay, 5d10, yeah, 6s2, 6p2, is this correct? Okay, just count, you'll get okay, 82, you'll get altogether how many electrons? 82 electrons. Now observe the valence electronic configuration of these carbon family elements. Okay, observe the valence electronic configuration. For carbon it is 2s2, 2p2, for silicon it is 3s2, 3p2, for germanium 4s2, 4p2, tin, okay, 5s2, 5p2, and lead 6s2, 6p2. Therefore, can I write the general outer electronic configuration of these carbon family elements as ns2, np2? Yes, the general outer electronic configuration of carbon family elements is going to be what? ns2, np2. Hope you understood. Okay, so what is the general outer electronic configuration of carbon family elements? It is ns2, np2. 2s2, 2p2 for carbon, 3s2, 3p2 for silicon, 4s2, 4p2 for germanium, 5s2, 5p2 for tin, and 6s2, 6p2 for lead. So the general outer electronic configuration is going to be, yes, ns2, np2. Okay, so I hope you understood about the electronic configuration. Now let us not rub this electronic configuration, because keeping these electronic configuration we have to explain the atomic radius, ionization enthalpy, and oxidation state. Okay, so shall we? Yes. So what is the general outer electronic configuration of these these carbon family elements? It is ns2, np2. So please don't rub this also. Okay, ns2, np2. Okay, because using this we will explain the oxidation state. Okay, using this we will explain what? The oxidation state. Understood? Now coming on to atomic radius. Yes, very important. Atomic radius. Okay, so what should happen to the atomic radius as we go down the group? Yes, as what should happen to the atomic radius as we go down the group? We know the atomic radius should increase down the group, correct? Okay, because electrons are added to different shell. Here the electrons are added to second shell, third shell, fourth shell, fifth shell, sixth shell. Since electrons are added to different shells, okay, different shells, and because of the shielding effect of the inner electrons, okay, the atomic radius increases down the group. This is the known fact. This is the known fact. Okay, I don't have to explain it again, correct? So as we go from carbon to lead, okay, as we go from carbon to lead, the atomic radius should increase. Okay, atomic radius should increase. Therefore, what is the expected atomic radius? Okay, the expected atomic radius, we are expecting the atomic radius to be carbon less than silicon, silicon less than what? Okay, germanium, germanium less than tin, tin less than lead, isn't it? This is the expected atomic radius. Okay, but this is not the actual atomic radius. No. Okay, the atomic radius does not vary down the group in this order. Okay, there is a change in the variation of atomic radius down the group. So what is the actual order of atomic radius? Okay, what is the actual order? This is wrong. This is absolutely wrong. Okay, don't just simply blindly tell that, okay, atomic radius increases from carbon to lead. Don't be blind enough. Okay, try to explain it with appropriate, okay, reasons, with subsequent answers. Okay, are you able to understand? I am telling you that, okay, now atomic radius does not increase down the group as expected. Okay, no doubt atomic radius increases from carbon to silicon, silicon to germanium it increases. Okay, germanium to tin it should increase. Yeah, germanium to tin it will increase, but the atomic radius of lead is less than that of tin. Look here, this is the actual atomic radius. This is the actual atomic radius of what? Okay, carbon family elements. Okay, I hope you are able to understand what is the change here. Down the group the atomic radius should increase. That means the atomic radius of lead is expected to be more than that of what? Tin. But what is actually happening here? The atomic radius of lead is less than that of tin. Correct? Okay, the atomic radius of lead is less than that of tin. How do you explain this phenomena? How do we explain this phenomena? Any idea? You know, we have explained this in boron family also. Okay, we explained this in boron family also. Okay, you know, we are expecting the atomic radius to increase, but okay, the atomic radius of lead is less than that of tin. Why? Understand? Okay, why the atomic radius increases down the group? Because of shielding effect. Because the electrons are added to different shells, okay, and because of the shielding effect the atomic radius increases down the group. Correct? Okay, but what is the order of shielding effect? S orbital will exhibit more shielding effect than p orbital. P orbital will exhibit more shielding effect than d and f. That means d orbital and f orbitals will exhibit poor shielding effect. Correct? D orbitals and f orbital will exhibit poor shielding effect. Okay, it will exhibit poor shielding effect, d orbitals. Okay, see, if you can observe that is why I retained the electronic configuration. I didn't rub this. Why? Because I have to explain the atomic radius based on this electronic configuration. Are you getting my point? Observe the electronic configuration of lead. Okay, observe the electronic configuration from tin to lead. Okay, see, from, you know, if you can observe the electronic configuration, you will observe completely filled d orbitals, completely filled inner d orbitals, okay, and f orbital, isn't it? Okay, there are completely filled inner d orbitals. Okay, inner d orbitals and f orbitals will exhibit poor shielding effect. Poor shielding effect. That means, okay, the shielding effect in lead is very, very, very less. Okay, because there are both inner d orbital as well as inner f orbital. D orbitals and f orbitals will exhibit very, very poor shielding effect. Very, very poor shielding effect. Since they exhibit poor shielding effect, are you able to understand? Here also the shielding effect is less. Here also the shielding effect is less. But in case of lead, the shielding effect is very, very, very less. Why? Because there are both inner d orbital as well as what? Inner f orbital. Therefore, the shielding effect is very, very, very less in case of lead. If the shielding effect is less, the outer electron will be pulled towards the nucleus. When the outer electron is pulled towards the nucleus, the atomic radius will obviously decrease. Will obviously what? It is going to decrease. Understand my point? That is why the atomic radius of lead will be less than that of what? Tin. Why the atomic radius of lead is less than that of tin? Okay, last time. Yeah, can you please explain why the atomic radius of tin is less than that? Sorry, lead is there less than that of tin? Because tin has electrons. Okay, tin has completely filled, okay, inner d orbitals and f orbitals, which exhibits very, very, very poor shielding effect. Because of the poor shielding effect of d orbital and f orbital, the outer electron will be pulled towards the nucleus. When the outer electron is pulled towards the nucleus, okay, the atomic radius will decrease. Got it? Okay, therefore I can say lead has less atomic radius than tin because of the poor shielding effect of both d orbitals and f orbitals. Okay, so carbon to silicon it increases, silicon to germanium it increases, germanium to tin it increases, but from tin to lead it decreases. Okay, no doubts? Okay, so next phenomena, what is it? Ionization enthalpy. Ionization enthalpy. Okay, yes, we know ionization enthalpy is inversely proportional to atomic size or atomic radius. Is that correct? Atomic size or atomic radius, correct? As the atomic radius increases, ionization enthalpy, sorry, as the atomic radius increases, ionization enthalpy decreases, isn't it? As the atomic radius increases, ionization enthalpy decreases, it decreases. Is that correct or not? Yes. Okay, so as we go from, okay, as we go down the group, atomic radius increases, therefore ionization enthalpy decreases. So that means the order of ionization enthalpy is exactly the reverse of atomic radius, isn't it? Okay, because ionization enthalpy is inversely proportional to what? Atomic radius. Okay, therefore the order of ionization enthalpy is the reverse of atomic radius. Therefore I can say carbon has more ionization enthalpy than silicon. Silicon has more ionization enthalpy than germanium. Germanium has a more ionization enthalpy than, okay, lead. Lead has more ionization enthalpy than tin. Here also the question might come. Why the ionization enthalpy of tin is more than that of, okay, sorry, why the ionization enthalpy of lead is more than that of tin? How do you account? Can you please tell me why the ionization enthalpy of lead is more than that of tin? Because in lead, okay, the shielding effect is very less because of the presence of d orbitals and f orbital. Since the shielding effect is very less, the outer electron will be, okay, more attracted towards the nucleus. The outer electron is tightly held to the nucleus. Since the outer electron is tightly held to the nucleus, the removal of the outer electron becomes difficult. That is why the ionization enthalpy of lead is more than that of tin. Okay, no doubts. Again, it is because of the poor shielding effect of d orbitals and f orbitals. Okay, no doubt with this, guys. Okay, so this is the order of atomic radius and this is the order of what? Ionization enthalpy. Now, what about their oxidation state? Okay, what about the oxidation states of, okay, carbon family elements? What about the oxidation states of carbon family elements? Okay, look here. See, what was the general outer electronic configuration of carbon family elements? It was NS2, NP2, isn't it? Okay, the outer electronic configuration of carbon family elements was NS2, NP2, 2s2, 2p2, 3s2, 3p2, 4s2, 4p2, 5s2, 5p2, 6s2, 6p2. Therefore, it is in general it is NS2, NP2. Correct? Okay, that's correct. So look here. So the elements, the carbon family elements have 4 electrons in their outermost shell. Okay, 4 electrons in their outermost shell. So these elements can either lose this outer p electrons, okay, and they can be in +2 oxidation state, isn't it? These elements of carbon family can lose the outer 2 electrons and account for +2 oxidation state, or else they can lose all the 4 outer electrons. When they lose all the 4 outer electrons, they will be in +4 oxidation state. Correct? They will be in which oxidation state? +4 oxidation state. Am I correct or not? Okay. So the carbon family elements can lose either the outermost 2 electron and they can be in +2 oxidation state, or else they can lose all the 4 electrons, okay, 4 outer electrons, and they can be in +4 oxidation state. Therefore, if I can speak about carbon, look here, if I talk about carbon, okay, so carbon can be in +4 oxidation state and +2 oxidation state. Okay, silicon can be in +4 oxidation state and +2 oxidation state. Germanium can be in +4, +2. Okay, tin can be in +4 and +2. Okay, lead can be in +4 and +2. Okay, so when do you say that they'll have +2 oxidation state? If they lose the outermost 2 electron. When do you say that they'll be in +4 oxidation state? When they lose all the 4 electrons. Okay, 4 electrons from the valency shell. Correct. But what about the stability of +4 oxidation state, and what about the stability of +2 oxidation state? Okay, what about the stability of +4 oxidation state, and what about the stability of +2 oxidation state? Yeah, look here. Yes, the stability of +4 oxidation state, okay, yes, the stability of +4 oxidation state decreases down the group, okay, whereas the stability of +2 oxidation state increases down the group. Are you getting my point? The stability of +4 oxidation state decreases down the group, whereas the stability of +2 oxidation state increases down the group. How do you account for this? Okay, that means the stability of +4 oxidation state decreases, whereas the stability of +2 oxidation state increases down the group. This means that, okay, look here, lead, if I take, okay, stannous chloride and stannic chloride. This is stannous chloride and stannic chloride, okay, lead chloride, PbCl4 and PbCl2, okay, which is more stable? We know tin and lead, okay, they are more stable in which oxidation state? +2 oxidation state. That means SnCl2 is more stable than, okay, PbCl2, correct? SnCl2 is more stable than SnCl4 and PbCl2 is more stable than PbCl4, correct? So here stannous is in +2 oxidation state, here stannous is in +4 oxidation state, here lead is in +2 oxidation state, here, okay, lead is in what? +4 oxidation state. Am I correct? Okay, lead is in +2 oxidation state, lead is in +4 oxidation state. So down the group we know, okay, +2 oxidation state is more stable than +4 oxidation state. Therefore, okay, stannous chloride is more stable than stannic chloride. PbCl2 is more stable than PbCl4. Correct? Yes. So, why SnCl2 is more stable than SnCl4? Why PbCl2 is more stable than PbCl4? That means, why the stability of +4 oxidation state decreases and why the stability of +2 oxidation state increases? Why it increases? Okay, now we know, we have understood down the group, okay, shielding effect decreases, correct? Okay, shielding effect decreases. Why the shielding effect decreases? Because of inner d orbitals and f orbitals. Okay, because of poor shielding effect, don't you think the outer shell will be near to the nucleus? When the outer shell is nearer to the nucleus, okay, don't you think the removal of electrons becomes difficult? Correct or not? The removal of electrons becomes difficult. Correct. Okay, see, from germanium, tin and lead, okay, there is poor shielding effect because of inner d orbitals and inner f orbitals, and because of the poor shielding effect, these three will experience what? Poor shielding effect. Okay, so because of poor shielding effect, okay, so these outer shell will be held tightly to the nucleus, they will be nearer to the nucleus. When they are nearer to the nucleus, the removal of the electrons becomes difficult. Okay, see, when they are nearer to the nucleus, the removal of the s electrons becomes difficult. The removal of s electron becomes difficult. Okay, why the removal of s electron becomes difficult? Because the s electron is tightly attracted to the nucleus. Since the s electrons are tightly attracted to the nucleus, the removal is very difficult. Am I correct? Therefore, I can remove only what? Outer p electrons. Okay, if I can remove only outer p electrons, okay, I can account for only +2 oxidation state. Okay, are you all able to understand my point? So as we go down the group, okay, +2 oxidation state increases. Okay, why +2 oxidation state increases? Because the removal of s electron is very difficult, since it will be tightly attracted to the nucleus. Therefore, s electron will not participate in the reaction, only p electrons will participate in the reaction. This is called as what? Inert. Okay, this effect is called as inert pair effect. Okay, so what is inert pair effect? Okay, the non-participation of s electrons, okay, towards bond formation is called as what? Inert pair effect. So s electrons will not participate in bond formation, only p electrons will participate in bond formation. That is why, okay, as we go down the group, the stability of +2 oxidation state increases, whereas the stability of +4 oxidation state decreases. Okay, so guys, with this, okay, in the next video we will talk about something more about the oxidation state, and then we'll go with the physical properties and the chemical properties of carbon family elements. Okay, yes, thank you.